product, sorry. So concentration of what? Uh-huh. Okay. And so they told you that the K was equal to 4.251 times 10 to the negative 2. So with that information and the water vapor concentration, water vapor was given to you as 0.990 or 1990 molar. Your job was to figure out where the hydrogen gas and the carbon monoxide gas was. But what you probably didn't realize is that some of you guys forget that whenever you form products, you don't get to choose which products to form. They are forming at whatever ratio the BCE says so. So in the BCE, it told you were forming carbon monoxide and H2, and at what ratio? 1 to 1, right? So 1 there, 1 there. So knowing that, you can actually say you're forming X amount of carbon monoxide and X amount of hydrogen gas because they're forming at the same ratio. That's why I just said 1x for each of those. So each of these are worth 1x. And so you can always solve for x. It's just algebra. So if you know your K value, you know each of these are worth 1x, x, and x over 0.1990 molar. Set that equal to the K value given, 251 times 10 to the negative 2. Then you can actually solve for the concentrations by solving for x. So tell me how you're solving for x here. Math, yeah.
So the CO for carbon monoxide and hydrogen gas are the same, so you can put squared next to x.
So this is x squared over that.
Yeah, and then you multiply the denominator.
And then
Square root it.
Okay, so I'm not going to go through all the math every time, but I'm just going to make sure I can talk it out. Denominator on the other, or multiply by the denominator on the other side, square root, you get x is equal to carbon monoxide, which is also equal to hydrogen gas, which is equal to 0.0919 molar. Yeah. All right, don't forget these are concentrations, so please put your units on. The concentrations, the K values themselves will not have values, all right? So you're good, units, you're good at that. 6, the only thing I did not give you in 6 was what? I didn't give you something, and you had to get it yourself. BCE. So when I told you phosgene decomposed to make carbon monoxide and chlorine gas, you already knew the BCE. You just had to write it out yourself. So what was the BCE? COCl2 equilibrates to what? Okay, so now you know the K expression is concentration of carbon monoxide times chlorine gas over, actually, is that cobalt? No, it's not. Okay. There we go. And your job was to figure out, based on what they gave you, what you didn't know. Did you know the K value? Yeah, you did. 282 times 10 to the negative 2. What else did you know here? You knew that one? You knew the cobalt, the CO and the CO2, didn't you? I don't know how what is the concentration of COCl2 when the concentrations of both carbon monoxide and chlorine gas are 5.90 times 10 to the negative 3rd? So what did you know?
CO and CO2.
You knew these two to be the same value. So you plug in the same value for both of those at 5.90 times 10 to the negative 3rd molar squared, because there's 2 of them, you multiply them together over x. So if you don't know a value, assign it to be the variable x and then solve for it. So, so then you probably moved your x over here and then divided whatever this squared was, divided by the K value. And you got x's concentration to be times 10 to the what?
Negative 4.
I whited mine out. I can't actually see that is all there. Okie dokie. And number 5, I bet you if you asked me number 5, you forgot to square everything. Or put parentheses around your numerator because there's a lot going on in the numbers there. Okay. So how do we feel about solving for x's? Not bad? Let's do a more complex x one.
Complex x.
More complex x. And I need some room here. Let me copy this. And then this is not on your paper anywhere. This is an example I did not get to yesterday. So please write down at least the BCE for this. Write down the BCE, and I'll show you how to solve throughout, okay? So this one's more complex. And a lot of this stuff, like this one's more, this is like my intro problem for AP Chem when we get to equilibrium. We do a lot more. We do 2 months of equilibrium. 2 months. We're doing it in 5 days. But we're not doing it at all. We're just doing the baby stuff. So we're going to get to a little bit more complex stuff tomorrow, but that's about it. So I'm going to stop there. So we have hydrogen gas and iodine gas yielding 2 hydrogen iodides or hydroiodic acid, however you want to call it. But in gaseous form, sometimes we don't name it by the true acid name. We name it by saying like hydrogen blank. So that's why you'll see the nomenclature is a bit different. You're starting off with 0.2 moles of hydrogen gas, 0.2 moles of iodine gas placed in a 1 liter flask. When the reaction was allowed to reach equilibrium, what concentrations of blah, 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 blah would occur? So what am I giving you? What conditions? Equilibrium? I'm giving you initial, right? I'm not giving you equilibrium. So if I give you initial, what do you automatically know you have to set up? Icebox, good. Because you don't know equilibrium, and you know your goal is always to get to equilibrium. So if I tell you blah, blah, blah reacts till equilibrium, you know I'm not giving you those values. And so another point to note is that always use molarity in ice boxes, okay? You have to have molarity. I gave you a really easy way to get molarity. What did I give you? Moles in how many liters? 1 liter, okay? So that's what molarity, what molar for this one? 0.2. Let's say, because you did 0.2 moles over 1 liter. If I had given you 2 liters, what would have been the molarity? 0.1. So, I mean, I can split up the values, or I can give it to you as molarity. That one's easy to get. 0.200 molar. Next one. Same, because it's the same moles. See? Iodine, 0.2 moles, same liter flask. Last one. Why do you know 0? Right, you have no products at the initial before the reaction has started. Sometimes you do, but in this case we're going to say we don't. And especially if I don't tell you, you get to assume 0. Do you know anything else? I mean, you know the K value. What else can you write out right now? Okay, we can do that. Just give me a second for that one. What else can we write out that's usually at the very beginning of the column you want to write out?
BCE.
It's already here. Expression, K expression. Give me the K expression. HI squared over. There you go. And I ask you to do that early because once you start getting into the icebox, you'll forget to write this, and if you do it really quickly, you'll forget the square. Just trying to protect you from yourself. All right, so we have our K expression set up. We don't know anything else. So I don't know what the end is. I don't know what the change is. So if I don't know that, I get to choose to include x's here. It makes your life easier. The variable x will be used all the time. Am I going to subtract or add to the reactant side? Subtract. How many x's am I subtracting from this one? Why 1? Coefficient is 1. It's a ratio. You're subtracting 1x here. How many here? 1x, because it's also a coefficient of 1 and 1. As I consume reactants, I'm making products. So what am I doing over here? 2x, right? I'm adding 2x simply because the coefficient is 2. It's related to the rate of reaction, kind of, or the way a reaction happens. You have 1 H2 and 1 I2 reacting for every 2 HIs formed. So your reaction stoichiometry is represented in coefficient form. So then at the end, I don't know anything else. I have to literally copy down what I just wrote. 0.2 minus x. 0.2 minus x, and 0 plus 2x is just 2x. There's my equilibrium. Why did I have to get to equilibrium before I could proceed? What's that thing called again? Equilibrium constant, right? You can't put anything but equilibrium in that. So our K value is 49.5. And we have our setup already. Now we can plug directly into that setup. What am I plugging in?
2x.
So 2x what? Squared on top. And? Why are you squaring it? There happens to be 2 of the exact same things, right? So H2 and I2 are both 0.2 minus x, and so we're just going to square that. Now, this isn't even chemistry anymore, right? We're going like hardcore math right now. Hardcore. Not calculus yet, but we're just algebra 2. Maybe. Tell me how to solve.
The two square roots cancel out.
No, you have to cancel them by doing what? What's the inverse of squared? Square root the whole shebang, right? Whatever you square, if you square root the right side, you have to square root the left side as well. Square root of 49.5 is 7.03. It's equal to, what is this reduced to? All right, and that's a little function together. You can't separate that function in the denominator. Now, keep going. We have to, change some stuff around, eventually combine like terms. Multiply by what?
0.2 minus x.
Okay, so 7.03 times the denominator, 0.2 minus x is equal to 2x. Because I just pulled that the denominator over there. Sorry, it's really close, but can you guys see what I did? Okay? Let me just scooch this down just a tad. Okay, now what's next? Okay, so that and that, so I believe that was like 1.408. 07. That times that minus 7.03 x equals 2x. And then keep going on the other side. So then you get 1.407 is equal to what? Yeah, because you're adding your 703 to 2. So that's 9.03x. And then dividing point by 9.03. X is equal to 0.1156 molar. I went faster than math because I'm not teaching you math. This is just implementing the math you already know. All right, so is that our answer? No, that's just the baby step to get us to the answer. What is our question? Everything at equilibrium, right? We're looking for the concentrations at equilibrium. So why do we solve for x? To the e values, right? So we're plugging 0.156 in for x. Oops, sorry, there it is right here. So you guys tell me what your concentrations are. I hear you on the first one. Hold on. So hydrogen and will equal the iodine because you're doing the same. 0.2 minus 0.156 is what? 0.044 molar. All right, and then the other one, what are you doing to find that one out? It was 2x, so it was 2 times value found here. So, thank you, 0.312 molar. So our answers are here for the hydrogen and the iodide separately, and here for hydrogen iodide. All right, so was that hard or was that just long? That was just, just tedious. You're going through all this math. Now, if you're like super savvy and you get me, maybe you get me here, or maybe to this point, and then you kind of just modify your math here to not show all your work, I'm fine with that. But if you mess up, that's on you, okay? I'm going to show my math as much as I can for you, just so you can kind of review that with me. All right, team? All right, so we're going to kind of do one more equilibrium problem a day. Tomorrow we'll go over Ka and Kb stuff. Let's do Le Chatelier's. What is Le Chatelier's principle? Loud and proud straw. When a stress is applied to a system, what? Okay, so scenario, you have equilibrium. You add a reactant or you add a product. Oh no, is it at equilibrium anymore? No, you've messed it up. Your job is to allow the equilibrium to reestablish. So if you add a reactant or product, it's going to shift left or right or no shift towards the reactants or towards the products to reestablish equilibrium. You're going to see that in the lab first, and then we'll come back and discuss, okay? The lab is very specific. I'm not going to help you a lot. I'm going to answer some questions. It's inquiry-based so that you're going to have your own aha moments. I had a couple of them in first period. It was great. So the only things I need you to do is so go ahead and get paper out. At the very beginning of the lab, you have to read the pre-lab, and you're going to write down the BCEs. If you do not write down the BCEs, then you're going to be lost. Make a note right now to say, write down BCE. The chemicals are colorful. There's orange, yellow, there's some brown. Don't get on your clothes because it will stain your clothes. 2 of them are carcinogens. Please do not lick your fingers or your lab partner's fingers or squirt them on each other. Make sure you reread procedures. There are a couple of things that look really similar. What is potassium chromate? Okay, that potassium chromate looks eerily similar to potassium dichromate. Please read it. I had people adding the wrong stuff, and I was about to set them down and give them a 0 in the lab, because it takes a while to prep this lab. 2 other caveats, or 2 things I need you to know, because the lab says differently. I'm going to pass out 10 milliliters of solution A to you, which is just a solution of combined things. I'm going to pass that out to you at your lab stations, and in the lab it says you need 10 mils of the potassium chromate and dichromate. You only need 2 mils. Make a note, I'll leave it up here too, but those are the carcinogens. So I'm just trying to minimize our carcinogen stuff out there, okay? And you guys know how to see the 1 milliliter graduation on the pipettes, right? They're the plastic pipettes, and they have 1 milliliter on there, because so you can really minimize the use of graduated cylinders. You don't have so much to wash at the end, okay? All right, same group as the collision theory lab. Go. Oh, 1 second. Benny, see me in a second at your station.
It was easier for me to type it out.
Yeah, come on. Hold on. Start videoing again. Okay. So that's why there was no shift there, because they're not involved in equilibrium. Okay, so no shift. Okay, last one, we have a separate reaction going from yellow to orange. As we added HCl, essentially what were we adding that was relevant for the reaction? Look in the reaction. H what? H3O plus, right? Hydronium. So HCl is essentially hydronium because it's a strong acid. What are you adding? A reactant or product? You're adding a reactant. See? A reactant right there. As you add a reactant, which way did it shift? It went from yellow to orange, correct? Right, it went to orange. It went right. So it's going towards the products because you're adding a reactant. So it shifted right. Then the second, when you added HCl, it went from yellow to orange. And then what happened when you added sodium hydroxide? It went from orange to yellow. Do you see sodium hydroxide in that reaction? No, but it caused a change, right? So what did sodium hydroxide, who did it mingle with? What did it do?
Water.
Okay, I can see it playing with water. I was going to say something else, but let me connect my dots and then I'll connect your dots. A base will always react with a what? An acid. So sodium hydroxide is reacting with what up there? It's reacting with a hydronium. When you react with a particular compound, it goes away, right? Because it's being reacted. So essentially, as you add the sodium hydroxide, you're reacting with hydronium. Hydronium goes away. So what have you done to the reactants?
Water.
You've decreased them, right? You didn't make water, but water is a pure liquid. Remember how in pure liquids in the equilibrium constants, pure liquids are irrelevant. Pure solids are irrelevant. That's why I'm straying away from water, because simply adding water does nothing. It's crap nothing. It's not related to equilibrium whatsoever. So I'm trying to get you to see the real reaction here. When you add a base to an acid, the acid gets consumed. It getting consumed does what to reactants? Goes down, right? You're losing reactants. Well, so what's the stress? You've decreased reactants. If you've decreased reactants, what do you want to do now? Produce more. So you have to shift left. So you have to go back towards the reactants. Simply adding base consumes reactants. Consuming reactants is a bad thing. You got to go back to the reactant side. The second case down here was the dichromate. We added sodium hydroxide. Adding a sodium hydroxide reacts with hydronium, and reacting with hydronium decreases reactants yet again. So decreasing reactants caused you to shift which way? Left again. Okay, so there's those. Let's talk about a couple of these analysis ones down here too. So The only two that we will here, let's quickly do these. Addition of product species does what? Just which way? Left, away from the products. You have too many products, you get rid of them by shifting away from them. Addition of reactant species shifts right. You have too many reactants, you go back to the left, to the right. Removal of product species, you go to the right to make up for that. Because you've lost products, you got to go back towards the products. Removal of reactant, shift left because you need to remake reactant. Now, endo and exo. So if you have an exothermic reaction, it's like A plus B yields C plus heat. Okay, heat is a product. If heat is a product and you increase the heat, what essentially are you doing? You're increasing the what? Products. Increasing products again makes you shift which way? Back to the left. So for the particular types of reactions, you have to write out heat either as a reactant or as a product so you can see it better. Increasing the heat of an endothermic reaction. Where's the heat? Reactant or product side? Reactant side. So if you increase a reactant, which way does it shift? To the left. I mean, right. Thank you. What if I had this exothermic reaction and I cooled it down? What am I doing? Taking away heat. So I'm taking away a product. Taking away a product will cause you to go which way? I have too few products, so no, I go back to the right. Okay, so if I cool down an exothermic reaction, the heat goes down. Oh no, I need more. Go back to the right. So you're always trying to right your wrongs. You're always trying to do something with that. All right, so you can write these notes on the same lab sheet. I will come back to that lab in just a second to finish the analysis. So we need to talk about all the conditions that can change equilibrium. 2 of them we've already accomplished. So we've already talked about changes of temperature. And changing the amount of reactant or product. We're going to talk about the rest of these now. Are the lights down okay? Is that okay? People in the back in the dark? You're not scared, right? Nobody's scared of the dark anymore? It's okay. It's just hard, really hard to see my board because it's kind of, the bulb is dying. So we already know that we can change temperature and it will influence equilibrium. We know we can add or remove reactant or product, and it will influence equilibrium. Write down the common ion effect, and then I'll give you an example of it. Thumbs up when you have common ion written down. Okay, so, because I'm going to show you an example before I move on to pressure. So, we previously said, oh, if the ion or the compound is not in equilibrium, it doesn't influence equilibrium at all, no shift. Sometimes things do influence equilibrium, like sodium hydroxide. It wasn't in the reaction at all, but it reacted with one of the things in the reaction. So therefore, it did affect equilibrium because it was like a kind of a 2-step process. So same thing with this one. On the analysis, you guys had a question, and some of you guys got to it, some of you didn't. That's why I'm reviewing analysis right now. If I can find my mouse, there it is. Okay. So on this one right here, you had a color that was a reactant that was pink, colorless, and then you had a product that was blue and then water, right? and you had to say addition of silver nitrate, silver or nitrate, neither of them are in this reaction. But silver is a heavy metal. It's very likely to form a precipitate with halides. So silver nitrate will cause chloride to come out of solution. What does that mean? And make, I just wrote it on the board just a minute ago. Silver chloride precipitate, okay? So if you pull chloride out of solution, you're making silver chloride precipitate. What does that do to that? All right, so that's the real story. It's decreasing that reactant. Which way does it shift? Left. Okay, so it's a two-step process. You have to say, oh, can this influence one of these guys in the reaction? Yep. It can precipitate out chloride. Precipitating out chloride means chloride goes away. I need to remake it. I go back towards chloride. Got it? So that is called the common ion effect. There's something in common that they have. So in that first one, addition of silver chloride should cause a color change back to pink. And then we'll go through the other ones in a second, maybe. So that's what this right here is talking about, if you want to write that down. That's what the reduced solubility means. Reducing solubility means forms a precipitate. And so the chloride was removed, so it causes a shift towards chloride because you needed to make more of it. All right, another example of how you can change equilibrium is changing the pressure, but it can come in two ways. You can either legit change the pressure or you can change the volume. Remember, volume and pressure are definitely related through Boyle's law. What's Boyle's law? P1, V1. Good. Increase the pressure on your box of air. Where's your box of air? You got it with you? Good. Okay, everybody brought it today? Brought it? Thank you. Okay, increase the pressure. What have you done to the pressure? What have you done to the volume? Made it smaller. Okay. So increasing pressure will also cause a decrease in volume or vice versa. They are indirectly related. So this is only relevant if you have gases in your reaction. So if I give you 2A gas equilibrates to 4D gas, you'll notice that I have 2 moles of gas on the reactant side and 4 moles of gas on the product side. It's only about the moles of gas. Solids and liquids they're not influenced by pressure. So if I increase the pressure on this system, your stress is that, oh no, you have too much pressure. Well, what's causing that pressure? Think molecular level. What's causing pressure? Collisions with the container wall, okay? If I have too much pressure, which of these scenarios is going to cause less pressure? 2 moles or 4 moles of gas? 2 moles, okay? So if you increase the pressure on the system, the stress you've done is you're too much pressure now, okay? So your goal is to shift to the side that's going to alleviate or relieve that pressure situation. Which way does it shift? Left, because less moles of gas. All right, so you got to connect some of these things together. What if I said increase the volume? What does increasing volume do to pressure? Right, it's like your volume's getting bigger, the pressure is getting lower. Okay, you're like, oh no, I have too low of pressure. I need to get pressure back up. Shift towards the 4 moles, right? Shift right. Shift right because 4 moles is greater than 2 moles of gas. So it's going to increase the pressure back up to the original equilibrium conditions. You're always trying to right your wrongs. You're always trying to go back to what it was. Do you get that? Yeah? Some of us? Heads are not shaking. Okay. Let's do another example. Oh, I need to talk about inert gas first. Inert gases are things like argon, neon, helium. What's the trend here you're seeing?
Noble gas.
Right, group 8 gases. Okay, they're all noble gases. They do not react. Or any other gas that's not present in equilibrium would be considered inert, no effect. No shift. Okay? All right, let's look at this example, and then I'll let you guys do something by yourself. Looking here, you'll notice it's all gaseous equilibrium. What else do you notice about this reaction? Right. So it's exothermic because the reaction has the product as heat, or heat as product. When you heat the reaction vessel, and the reaction vessel is just literally the container that the reaction is taking place in, okay? Heat the reaction vessel. What have you done? Increased what? Temperature, which is essentially a product. So what happens? Which way? Raise your hand if you say shift right. Thank you. Shift left. Okay. Because if you increase heat, you're increasing a product, and I say product in quotes because it's not really a product, it's just there. So increasing a product, so you need to shift away from products because now you have too many products. That's why you have to shift back to the left. Increasing pressure. What do you need to do right now before we can answer this question? Yeah? For an exothermic, it's a product. For an endothermic, it's a reactant. You have to look specifically at which type I'm getting to. So if I increase the pressure, how are you going to know which way it's going to shift? BCE, moles of gas. How many moles of gas over here? 4 moles of gas. How many over here? 2 moles of gas. Okay? So you increase the pressure. Oh no, too much pressure. Why shift right? Good. Shift right, less moles of gas. That's just a little helpful tip, making sure you know why you would shift to the right. If you remove ammonia, why shift right? So you lessen the products by removing ammonia. You need to get it back up. So your job is to make more products. Need more products. Okay, adding excess hydrogen gas. Why shift right? Yeah, you have too many reactants. How are you gonna get rid of them? Don't go towards the reactants. That's an extreme. You're making too much. So shift right to react excess H2. Decreasing the volume. Which way? Why are you shifting left? So I'm sorry. I know you can't see that. Let me go like that. Maybe that's a little bit better. Nay. Dang it. All right. Well, decreasing the volume does what to pressure? Increases the. I'm sorry. It increases pressure. Yeah, because when you squish your volume down, you've got too much pressure now.
So it's gonna go to
Right. We've already seen what happens when we increase the pressure.
Yes, shifting towards the side with less moles of gas. Because if you've decreased the volume, you've also increased the pressure. Your job is to alleviate that pressure. Alleviating pressure means less moles of gas. So shifting right. Okie dokie. Okay, you guys have 4 questions right now to do on that, and they look like that. It's on your lecture sheet. If you've already started that, also start the worksheet 2. Guys, pull up both things for you. Now pull up the lecture problems. That's like 2 to a page. You got those? Yep. Let me find one. So 2 to a page. At the very bottom down here, it says Le Chatelier's practice. 1, 2, 3, 4. Circle those. Those are you can do right now. And then on the worksheet, that looks like it's 4 to a page, and it says worksheet 2, Le Chatelier's principle. Do you see that one? You're doing 1 through 5, okay? And just write SL for shift left, SR for shift right, NS for no shift, or circle them 1 through 5 on this one. Okay. Yeah. If you're done with all the analysis, you can turn it in. If you're not, we'll turn it in later. So you have 9 Le Chatelier's problems. Get her done.
Is there anything else?
Oh,
You guys okay? You got to do? There's at 10 minutes. You can probably knock out half these at least. Maybe I'm overzealous. There's a quarter of them. The iodine ones? And you got one of them.
You're adding sweet and
I'll be right back.
They can get a little more. It gives you a 20. You're like, no, you deserve it. I will not start this. If you want us to do worksheet 2 for worksheet 2 or do 5.
little of something, you gotta be more. So you have to go to them. Maybe more. Really dark.
I got a register.
Basically telling you that energy is produced once you're actually positive positive, so it's being released.
Yeah.
Energy is more so early on the energy is so it's released. So it's released, so energy is released as a product, it's expansion. So you increase the you increase the possibility of that too much of this. You gotta get rid of it. So if you think it's out of it gives me a so close that. It means no reaction. Like that, like no
I don't know, what about the observation?
You and him not even related.
No change, but I think one with
Hold on. I just have to check the time. And I'm still videoing.